Hello everyone, welcome to this session. In this session, we will talk about a new concept, constraints, and its relation to objectives. So here is the optimization function, right? So we have a minimize, there's a fx. I want to find the minimum value of this with x within this search range from -3 to +3. Here we have another thing. We call it constraint. We call it subject to gx equals to x minus 1.5 larger than or equal to 0. It means that we need to, under this condition, now this is satisfied, then we minimize the value of fx. So this is different from the previous problems, and there is only one objective function. So we can see this. If we draw the fx here, we can see it's here, and so only in this side is gx larger than or equal to 0. So we call this one, we call it this area, we call it a feasible space. So feasible space means that the set of all possible solutions satisfying the constraint. So here is gx larger than or equal to 0, right? So in the feasible space, the solutions, we call it feasible solutions, right? So feasible solutions. Now we understand the constraint optimization. Then the question comes, now I have 4 solutions, solution 1 to solution 4. Each one have a different value of x. And here is the fx value, and here is the gx value. The question is that which solution is the best, and how to compare them. And you can see this for a while, right? So for the first 2 solutions, there are 2 different fx values, but all of the gx values are smaller than 0. It means that these 2 solutions does not satisfy the gx constraint. And for the solutions 3 and 4, the gx constraint is satisfied, right? And we have 2 fx values. So then which one is the best? Okay, now let's see how to compare them first. Given this problem, when we randomly pick 2 solutions, there are only 3 conditions. The first condition, both of them are feasible solutions. The second condition, one of them is feasible while the other is infeasible. So remember, feasible solution is a solution in the feasible space which satisfied the constraint. The third condition, we have 2 infeasible solutions. Then, in these conditions, what will happen? So let's see what will happen. So when we have 2 feasible solutions, because they are feasible, right? So we only compare the objective function value to find the better one in terms of objective function value. So here is minimization, so we want to find the smaller one. And when there are one feasible solution and another is infeasible, we always think the feasible solution is better, because we want to minimize this objective function under the condition of the constraint can be satisfied, right? So the feasible solution is better. So when we find 2 infeasible solutions, what we will do? We compare the constraint violations. The one with the smaller constraint violations is better because it's nearer to the constraint satisfaction, right? So these are the conditions. So based on these, that we can understand which of the solution is the best. First, we need to find the feasible solution. They are better than the infeasible solution. Then among the 2 feasible solutions, we find the one with a better objective function value, right? Okay, so now we have for the optimization problem, besides the decision variables and the objective functions, we added a new thing, constraints, right? So what are the difference between objectives and constraints? So for an objective, we say the smaller the better if we considering a minimization problem. And for maximization, the larger the better, right? But for constraint, this is different. We only consider is feasible or infeasible. So if they are both feasible, the feasible solutions in terms of constraint, they are considered the same. So then we will go to the objective function. So if for infeasible solutions, they are different because the constraint violation will decide which one is better, right? Okay. So just now, I only showed one constraint. So in the real-world problems, we can have many constraints. So this is a real-world problem. So this is an analog amplifier. So if you are electronic engineers, microelectronics engineer in the future, focusing on analog IC design, you will see this problem, right? This is then you can solve this problem by using optimization techniques. So we can see we want to minimize the power. These are all the specifications, right? We call it a performance matrix. So if we meet them, we minimize the power. So at this moment, analog circuit design is very complex. We need many experience. But after learning this class, you understand this problem, we can transfer it to an optimization problem. And by using AI techniques, we can solve this problem. So we can see you have multiple constraints. Okay, that's all for this session. Thank you very much. Bye-bye.